In this video, I am going to solve the problem 68 from chapter 19. At what frequency would be the wavelength of sound in air be equal to the mean free path of the oxygen molecules at 2.5 atm pressure and 0 degrees Celsius? The molecular diameter is 3 multiplied 10 power minus 8 centimeter. Here in this question, we are going to calculate the frequency. So here for this, we have to consider the speed of the sound in air, as well as we have to use the mean free path. Clear? So here mean free path is nothing but lambda, and the pressure information as well as the temperature information as well as the molecular diameter details are given here. So by using all these, we are going to calculate the value of the frequency. So for that, first of all, I'm going to write the given. What is given in the question? The diameter of the molecule is given, which is 3 multiply 10 power minus 8 centimeter. If you convert this in terms of meter, you will get 3 multiply 10 power minus 8 multiply 10 power minus 2, because we have to convert the centimeter to meter. By that, you will get the diameter value as 3 multiply 10 power minus 10 meter. Pressure information is given in terms of atm. So 2.5 atm, we have to convert this atm in terms of Pascal by multiply 1.01 multiply 10 power 5. So 2.5 multiply 1.01 multiply 10 power 5. We will get the answer of the pressure in terms of Pascal, which takes the value of 2.525 multiply 10 power 5 Pascal. And temperature, they mentioned 0 degrees Celsius. If you add 273, we will get the temperature here as 273 Kelvin. And the most important thing here, we have to consider the speed of the sound in air. So here the temperature is mentioned 0 degree. At 0 degree, the speed of the sound takes the value of 331 meter per second, because the sound speed will vary according to the temperature, right? So at 0 degrees Celsius, the speed of the sound takes the value of 331 meter per second. Clear? Okay. Now we have to write the basic rule for the speed. Speed v, which is equal to frequency multiplied by lambda. And here we are going to calculate the value of the frequency. Therefore, frequency, which is equal to speed over lambda. And lambda is here is nothing but the wavelength, but mean free path is also the lambda value. So I am going to use the mean free path here. Therefore, f, which is equal to speed over 1 over root 2 pi d square n over v. This is the rule for the mean free path. Okay. Now we are going to substitute the value here. So before that, we have to identify what is this n as well as v. Here the caps n stands for number of molecules, right? The caps n stands for number of molecules, and v is the volume. So we don't have this information in the question. So for that, I have to use some small substitution. Here in theory, we studied the rule for the number of molecules. What is the rule for number of molecules? The number of molecules, which is equal to the number of moles multiplied by Avogadro number, right? So we can use this value here. If you substitute the value here, we will get the answer. And also we have to use the ideal gas equation, PV, which is equal to N or T. Okay, first of all, I'm going to substitute. Okay, we have to rearrange this equation. By that, we will get the clear idea. If you rearrange this equation, this part will come to the top, right? So by that, this frequency will become V multiply all these terms will come to the top, right? So root 2 multiply with pi multiply with d square multiply with n over v. Now I'm going to take this and substitute this value here. So once you substitute this n value here, what will happen? This equation will change as v root 2 multiply by pi multiply with diameter square multiply with because here n takes the value of Na, right? So this part will become as n multiplied by Avogadro number over V. So here what I'm going to do, in this place I have to do some substitution. For that I'm going to take this ideal gas equation. What is this ideal gas equation? Pressure volume, which is equal to the number of moles multiplied by gas constant multiplied by temperature. So I'm going to use this ideal gas equation. So if you rearrange this equation in terms of N over V, number of moles over volume, will give the value of pressure over RT. So I have to take this and I have to substitute here. If you substitute, this equation will become frequency, which is equal to P, which is speed of the sound in here at 0 degrees Celsius, multiply √2, multiply pi, multiply d square, multiply, in this N over V, I am going to use this P over RT, right? So P multiply Na over RT. Now I am going to substitute the value. We have all the values here. So let's substitute one by one. F equal to, the speed of the sound in air at 0 degrees Celsius is 331. So 331 multiply with √2 multiply with pi. And what is the diameter of the molecule? The molecular diameter is 3 multiply 10 power minus 10 meter. I have to use this value here. 3 multiply 10 power minus 10, because it's square, right? So I have to square this, multiply with, what is the pressure? We already convert that pressure in terms of Pascal, so which takes the value of 2.5 atm. So when you convert this 2.5 atm in terms of Pascal, we got 2.525 multiply 10 power plus 5, right? Yeah, 10 power plus 5, and multiply with Avogadro number. What is Avogadro number? It's a constant, 6.02 multiply 10 power 23 divided by, because everything is in multiplication form here, right? Everything is in multiplication form, divided by the gas constant 8.314 multiply, the temperature is mentioned as 0 degrees Celsius, so we converted to Kelvin, which is 273 Kelvin, which is 273 Kelvin. When you divide all these, and after you, when you multiply all these, and after that, if you divide with this 8.314 multiply 273, we got the frequency as 8.86 multiply 10 power plus 9, and the unit for the frequency is hertz. Right? That's it. Thank you.